The human perception of time is fundamentally linear, bound by the rhythm of seasons, calendar dates, and the surface stillness of the Earth. We build cities, lay down highways, and plan generations under the assumption that the ground beneath our feet is a fixed, unchanging foundation. Yet, the geological record reveals a profound paradox. The greatest structural loads on this continent are accumulated in total silence, completely detached from the sensory awareness of the human beings walking above them. In the winter of the year 1700, this illusion of permanence was shattered in a single night when the entire Cascadia subduction zone ruptured along its full length, instantly dropping the coastline of the Pacific Northwest and displacing an entire ocean basin to send a massive wall of water thousands of miles across the Pacific to Japan. There was no macro-seismic warning that night, but there was a mechanical beginning, a multi-century phase of silent tectonic loading that no human alive could feel or quantify. Today, the technological framework has fundamentally shifted, allowing us to monitor this exact same system as it approaches its physical limits. This very week, high-precision instruments deployed along the West Coast detected and logged exactly 20,634 individual tremor events concentrated at the deep base of this identical fault system. The overwhelming majority of this seismic activity is clustered tightly at the southern end of the zone, while satellite geodesy confirms that the overlying coastline is rising millimeter by millimeter, behaving precisely like an elastic spring under continuous, severe compression. This is not a separate fault operating under a new physical mechanism. It is the exact same geological machine executing the identical loading sequence that preceded the last great megaquake. The critical baseline question for systems analysis is no longer if the structure will fail, but precisely which page of this mechanical timeline we are currently standing on. The defining systemic anomaly of the modern Cascadia subduction zone is the profound disconnect between instrument data and human sensory perception. Right now, the most hazardous fault system in the United States is undergoing significant displacement without generating standard high-frequency earthquakes or triggering public emergency alarms. Over a standard 7-day observation window, deep-seated instruments spanning from Northern California up into Washington recorded 2,634 distinct tectonic tremors along this single lithospheric boundary. Tremor, as a distinct geophysical phenomenon, operates on mechanics entirely separate from standard earthquakes. It represents a low frequency, drawn-out seismic murmur occurring deep within the transition zone where elevated temperatures and lithospheric pressures prevent the rock from experiencing brittle failure. Instead of snapping violently, the deep rock experiences slow, episodic slip events that remain completely undetected by human senses. A person walking the coastline of the southern margin occupies an environment of absolute perceived calm, while the underlying geological architecture is straining under an accelerating load that digital networks are actively registering as a severe spike in activity. This persistent silence is not an indicator of structural stability, but rather the primary mechanical indicator of a highly coupled, locked system. Within the strict framework of load distribution, these 2,634 tremors do not relieve regional stress. They systematically transfer it. As the deep plastic zone of the subduction interface undergoes slow slip, the accumulated strain is shoved directly upward onto the shallower, cooler section of the fault known as the locked zone. This upper segment is firmly welded by friction and static pressure, completely refusing to creep or slide. Consequently, every single low-frequency tremor recorded at the base acts as a direct mechanical input, winding the upper elastic spring tighter and increasing the total stress concentration on a structure that has been accumulating energy for 326 years. The current data indicates this is not standard background variation, but one of the most intense phases of quiet structural loading observed all year. matching the scale of the major strain surges documented between March and April of 2026. The localized concentration of these tremors at the extreme southern margin, beneath southern Oregon and northern California, directly exposes the primary structural fault line of the entire West Coast, raising a fundamental question about the hidden mechanics driving this specific segment toward its ultimate load limit. To evaluate the true threat of these 2,634 microsignals, the entire system must be viewed as an enormous slow-motion grinding machine that has operated just off the coast of the Pacific Northwest for millions of years. This lithospheric engine is driven by the relentless convergence of tectonic plates. Off the coast of Northern California, Oregon, and Washington, an oceanic slab known as the Juan de Fuca Plate, and its highly stressed southern component, the Gorda Plate, is being shoved directly into the North American continent. Upon impact, this oceanic floor does not pile up or deform outwardly. It undergoes subduction, bending downward at a shallow angle to dive deep underneath the much larger continental plate. The boundary where these two massive structures grind past each other forms a vast, slanted plain hundreds of miles long and tens of miles deep. The Cascadia subduction zone. The mechanical behavior of this immense contact interface is dictated entirely by depth, temperature, and pressure. At the deep base of the fault, elevated temperatures render the rock plastic, causing it to ooze and slide in the slow, low-frequency pulses we record as tremor. But as the fault ascends toward the cooler, brittle layers near the seafloor, the rock locks completely. In this upper zone, friction and extreme lithospheric pressure weld the two plates into a single immovable mass, halting all relative motion. This spatial divergence creates a critical systemic crisis. The bottom of the machine is moving while the top is completely stuck. Because the oceanic plate behind it never stops shoving, the strain cannot dissipate. Every time the deep plastic base slides during a tremor surge, it turns the screw on the locked zone above, forcing the brittle continental edge to bend, deform, and store the transferred energy like a giant spring. When the friction holding this locked zone eventually reaches its absolute structural limit, the entire boundary will snap forward in minutes, releasing centuries of accumulated strain in a catastrophic magnitude 8 or magnitude 9 earthquake. This is the exact mechanism that triggered the devastating magnitude 9.1 Tohoku disaster off the coast of Japan in 2011, where a highly coupled subduction zone failed under identical loading conditions, shifting the coastline feet to the east and displacing an entire ocean basin to unleash a catastrophic tsunami. The Cascadia subduction zone possesses the identical structural capacity. Yet for decades, a dangerous scientific myth persisted that this quiet system was safe. Early researchers assumed that because Cascadia did not produce frequent small earthquakes, the plates were sliding smoothly past one another. Systems analysis proves this logic was entirely inverted. The absolute silence was not an indicator of safety, but the definitive warning sign of a completely locked interface storing maximum energy. This systemic threat is further compounded by a profound cultural deficit. The average inhabitant of the West Coast associates earthquake danger exclusively with the San Andreas Fault, a famous sideways slip boundary that at its absolute physical limit cannot exceed a magnitude 7.9 and cannot generate a major tsunami. Cascadia remains largely anonymous to the public, hiding in the shadow of its smaller neighbor, despite being orders of magnitude more powerful. This lack of public awareness is a critical variable in the regional risk calculation. The danger is not obscured by a conspiracy, but by a massive lag between scientific discovery and public infrastructure, leaving a highly dense human population living directly on top of a highly compressed, silent geological spring that is actively being loaded toward its breaking point. The spatial concentration of the current seismic surge exposes a highly critical structural anomaly. The 2,634 tremors recorded this week are not distributed evenly across the 1,000-kilometer margin, but are heavily concentrated at the extreme southern end of the subduction zone. This localized loading is driven by a complex, high-pressure geological intersection beneath the southern coast of Oregon and Northern California. Here, the subducting slab is the Gorda plate, a smaller and significantly younger tectonic fragment than the main Juan de Fuca plate to the north. Because it is highly compressed and physically constrained by surrounding structures, the Gorda plate does not descend smoothly. It undergoes intense internal deformation and cracking as it forces its way beneath the continent, accelerating the rate of local strain accumulation. This regional stress field is further aggravated by two major offshore structural features that act as direct mechanical energy inputs into the southern segment. First, the Blanco fracture zone, a highly active transform scar in the ocean floor, grinds directly against the southern terminus of the subduction zone, continually transferring lateral shear stress into the system. Second, the Gorda Ridge, an active seafloor spreading center, exerts a constant outward volcanic push that drives the Gorda plate relentlessly eastward into the continental margin. These three distinct forces, internal plate deformation, lateral transform friction, and spreading center propulsion, converge directly upon a single segment of the coast, explaining why the southern margin is loading significantly faster and harder than the rest of the system. This structural disparity is clearly reflected in long-term probabilistic models. Geophysical assessments indicate that the probability of a major rupture occurring on the southern segment within a 50-year window stands at 37 to 42%, whereas the probability for the northern segment off Washington drops to roughly 7 to 12%. The data reveals that the southern margin is 4 to 5 times more likely to fail in the near future, aligning precisely with the intense tremor clustering observed this week. Furthermore, the geological record dismantles the superficial assumption that the Cascadia subduction zone only ruptures in full-length, 1,000-kilometer megaquakes. Deep-sea sediment cores extracted from the continental slope contain distinct layers known as turbidites, historical records of massive earthquake-triggered underwater landslides. While some turbidite layers span the entire length of the margin, a significant number are strictly confined to the southern segment. This physical evidence confirms that the southern end operates on its own independent clock and frequently fails in isolated, partial ruptures. These segment-specific events are major catastrophes in their own right, capable of generating magnitude 8 class earthquakes and severe local tsunamis without waiting for the rest of the fault to reach its limit. Every microseismic slow-slip surge documented in the year 2026 does not guarantee an immediate rupture, but it systematically advances the southern locked zone closer to its ultimate mechanical breaking point along a strict, one-way trajectory of stress accumulation. We are observing a distinct tectonic segment with an independent history of frequent failures being driven at an accelerated rate by converging offshore mechanisms. Yet the overarching human system built directly above remains fundamentally disconnected from this physical reality. The structural deformation of the Cascadia system is no longer confined to the domain of deep, invisible tremor counts. It has manifested as a measurable, vertical displacement of the physical landscape. High-precision geodetic instruments bolted directly to the continental bedrock have confirmed that the southern coast of Oregon is actively rising out of the ocean. This vertical displacement is recorded in precise millimeters, tracking an unyielding upward trajectory that has been monitored continuously for nearly 2 decades. At a primary monitoring station located near Brookings, Oregon, positioned directly above the highly coupled southern locked zone, the data is mathematically unambiguous. The landmass has risen approximately 60 millimeters since the initiation of its continuous dataset in the year 2008. To a casual observer, An uplift of 60 millimeters under 2 inches across nearly 20 years may appear negligible, yet within the framework of geomechanical engineering, the vertical displacement of millions of tons of solid rock and soil represents an immense accumulation of potential energy. This regional uplift completely dismantles any superficial interpretation, attributing the ground movement to localized volcanic inflation or magma chamber migration, as there is absolutely no volcanic signature present beneath the Brookings sector. Instead, the physical law of elastic deformation dictates that the overriding continental plate is being violently dragged downward and forward by the subducting oceanic slab, causing the edge of the continent to bow upward like the tip of a diving board under severe pressure. This structural distortion serves as definitive, empirical proof that the underlying tectonic spring is being compressed. The deep tremor surges occurring at the base of the fault and the vertical deformation recorded at the surface are two distinct expressions of a single, highly integrated mechanical process. The lower fault slides quietly, transferring its load upward while the locked zone resists, causing the land above to bulge in response. The danger inherent to this compressed state lies in the mathematical certainty that an elastic spring cannot store energy indefinitely. When the static friction of the locked zone drops below the accumulated stress threshold, this multi-century deformation sequence will instantly reverse. In a single co-seismic convulsion lasting mere minutes, the coastline will drop by several feet as the continental margin snaps back to its baseline equilibrium, generating a catastrophic regional displacement of the overlying ocean water. This abrupt seafloor displacement will instantly produce a major tsunami targeting the adjacent coastline. Because the primary fault plane sits immediately offshore, the travel time of the initial wave to high-exposure zones like Brookings and Gold Beach is compressed to a critical window of 15 to 30 minutes, eliminating the possibility of distant open ocean warning protocols. The 60 millimeters of geodetic uplift logged since 2008 represents merely the most recent fraction of a strain budget that has been accumulating uninterrupted since the last full structural discharge in the year 1700. For 326 years, this lithospheric machine has been steadily wound, and while modern instrumentation cannot calculate the exact second of failure, the strict physics of load accumulation dictates that every registered tremor and every millimeter of vertical displacement advances the system toward an inevitable high-velocity release. The structural validation of this tectonic hazard rests upon an extraordinary forensic convergence that reconstructed the catastrophic events of January 26, 1700. For generations of modern development, the absolute absence of a written seismic record along the Pacific Northwest led to the superficial assumption that the Cascadia subduction zone was entirely benign. This long period of silence was misinterpreted as safety, rather than what it truly was: the absolute lock phase of a massive structural spring. The deconstruction of this myth began with the discovery of ghost forests along the tidal flats of the coast. Stands of ancient red cedars that died simultaneously when a sudden subsidence event dropped their root systems directly below the saltwater tide line. This terrestrial evidence matched extensive sand sheets washed far inland by a massive paleotsunami. The definitive chronological anchor, however, was found across the ocean in Japan, where ancient administrative archives documented an orphan tsunami that struck the coast without any preceding local earthquake shaking. By matching the tree ring data of the drowned forests with the precise Japanese arrival logs from the year 1700, scientists confirmed that the entire 1,000-kilometer fault had ruptured in a single magnitude 9 convulsion, dropping the coastline, losing entire indigenous villages, and sending a wall of water across the open ocean. This deep historical baseline transforms the current 2,634 tremors into an explicit mechanical preview. We are analyzing the exact same structural machine, operating within the same cyclic boundaries. The geological record preserved in deep-sea turbidite layers shows that Cascadia has undergone approximately 20 of these massive discharges over the last 10,000 years, establishing an average recurrence interval of roughly 500 years. Having accumulated stress for 326 years, the system has entered the statistical window where structural failure is possible, and every slow slip event systematically advances the locked zone toward its maximum load capacity. The ultimate crisis emerges when this planetary mechanism intersects with modern infrastructure and human unawareness. In places like Gold Beach, Oregon, field interviews reveal a profound knowledge deficit. Residents routinely assume regional earthquake risk is confined to the distant San Andreas Fault, remaining entirely unaware of the high-velocity subduction interface sitting just offshore. This lag in risk perception creates a catastrophic vulnerability. A rupture along this highly coupled southern segment will cause 4 to 6 minutes of continuous, violent low-frequency shaking capable of liquefying river-valley soils, collapsing unreinforced structures, and triggering massive landslides that will sever the region's isolated coastal highways. Within 15 to 30 minutes, before any distant alert protocol can function, the co-seismic drop of the seafloor will launch a massive tsunami directly into these unhardened coastal towns. Modern technology has provided critical defensive buffers, such as the MyShake early warning network, which detects rapid primary seismic waves to provide citizens with crucial seconds to drop, cover, and hold on before the destructive secondary waves arrive. However, technology cannot alter the absolute physical boundaries of the system. The ongoing 2,634 tremors, the 60 millimeters of geodetic uplift, and the historic multi-century strain budget represent a fixed mechanical progression towards structural discharge. The physics of the Cascadia subduction zone dictate that the compressed spring will inevitably release its stored energy, and the survival of the human population depends entirely on closing the gap between the silent reality of the instruments and the awareness of the communities living on the edge of the continent.